Hi everyone, welcome to RPi Data Science. So last time we talked about measures of effect sizes in single group design. So we have seen different effect sizes such as mean, proportion, correlation, and also we didn't touch, of course, it's like the regression coefficients. They can also be considered as effect size measures in single group designs. Although they tell you some relationships, but regression coefficients can also be considered as effect sizes in single group designs, especially if they are not telling you anything between like control and experimental group. They are really telling you only the single group designs. They can be considered as part of effect sizes in single group designs. So for today, I would like to extend that to in control group designs. So the today's session will be about effect sizes in control group designs. That's what I would like to talk today. Yeah, so the first thing I want to talk about today is continuous outcome actually. So for continuous outcomes, the first thing you need to ask is how the scale of the measurement is, whether the scale of the measurement is similar or not. Anyway, there are three main types of continuous outcome effect size measures. One is mean difference, standardized mean difference, and ratio of means. They are really these are the very popular ones, mean difference and standardized mean difference. And ratio of means, I haven't seen it actually many times that being used in meta-analysis, but these are the most popular ones. Anyway, the first thing you need to ask whether to use mean difference or standardized mean difference, what to choose. So the first thing you need to ask is whether the scale of measurement is similar or not. So if the scale of measurement is similar, for example, height is measured in kilogram, I mean height is measured in centimeters from one study to the other, it's exactly the same scale, then you need to stick with mean difference. Or weight is measured in kilograms, and again, it's the same from one study to the other. So you have to stick with, again, mean difference. Like the same is true for glycated hemoglobin levels, HbA1c. So if HbA1c is measured, if you have 7 studies, and if 7 of them measured it in percent, then you don't have to use standardized mean difference, you can simply use mean difference. But for other outcomes, the scale of measurement may be different because of the tool difference or the unit method of measuring difference. For example, if depression is measured using the Hamilton Depression Index or other depression measures. So if you have multiple scales to measure depression, so if it differs from one study to the other, because your goal is to pool or to meta-analyze them, then you have to choose a different effect size measurement. That one is a standardized mean difference. So that means you need to standardize them so that they can be similar across. The measurement will be similar across measurements. Otherwise, combining them will be combining apples with oranges. And the other one is quality of life. So quality of life may be measured in SF36 or SF8 or SF12. There are many different quality of life measures. All of them plan to measure quality of life, but the scale of measurement is different. In that case, you need again to use standardized mean difference. You need to standardize them before pulling them. The next one that I want to highlight is within the continuous outcomes with the mean difference. So that one is between group mean difference. For example, if you have a randomized control trial, you have intervention group and experimental group. So that means you use between group mean difference. The difference of differences, like a mean difference in control group and then the difference in experimental group, and then you subtract the difference between the two, and then you get the between group mean difference. That will be a raw mean difference. It's not standardized. It's as it is. The unit will stay the same, and it's unstandardized mean difference between two groups. That's called between group mean difference. In some cases, you also will probably use within group mean difference, especially if you use studies like in pre-post studies, before after studies, like before the intervention and after the intervention. For example, if you have exercise trial, physical activity trial, and then after for example, I don't know, heart rate or something, for example, heart rate or respiration rate before the exercise and after the exercise. So for example, if the heart rate before the exercise was 70 and after the exercise if it is 90 or 100 or something, then you get this pre-post, and that is called within group mean difference. We'll talk about that, but for now let's stick with between group mean difference. So between group mean difference, again, it should be to use the between mean group difference, you have to have exactly similar scale. So that means from one study to the other, it should be in similar scale. Otherwise, it will not be right to combine them with this kind of effect size measure, which is between group mean difference. So to measure effect sizes in control group designs for continuous outcomes, so as I said, the mean difference. So you calculate the mean difference, the between mean difference, and that one will be the mean at the intervention group minus the mean at the control group, or for example, the mean in group 1 minus the mean in group 2. So you get the mean difference. So because the standard deviation is very important here for combining the studies. So the way studies will report mean and standard deviation in one, and then the mean and standard deviation in the other. So you need to use pooled standard deviation, and that pooled standard deviation is calculated by this formula. And then once you have this pooled standard deviation, if you want, you can also calculate standard errors, and that's how standard error is calculated. And let me just do a quick demo to continue this. And I will simply display my R. Let me go back to R. So the pooled standard deviation is already changed into a function. So we have this formula, and I already changed it into a function. So we calculate the mean difference and pooled standard mean difference. So let me just create a random sample of 100 observations with 2 different means and 2 different standard deviations. So let me just use let me reducible to be exact. Let me just use set seed. So set seed, let me simply 1 to 3, and then let me create group 1. So that means let me just simply call it x1. X1 actually. Yeah, okay, let me call it x1. So then I will consider the R1 that R offers. So this function requires the number of observations. Let me just call 100, and the mean is supposed to be, let me just give it 20, 25, and the standard deviation, let me just make it 5. And let me create another one, x1, and that one again I will call it 1, and let me just again make it similar sample size, and then after that let me just make the standard deviation to be, I mean to be 20, and then the standard deviation to be about just 3.1. Now I have this, so I already get this, run this, and then I will get my sample distributions for x1 and x2. Oh, okay, x1, x2, x2. So I will have two different sample sizes for x1 and x2. And then once you have that, let me calculate the mean one. The mean one would be the mean of x1. We already defined the mean has to be 25, but this is a random sample. It cannot be exactly 25. I mean, if we have really large sample size, maybe 1 million or something, then the mean of this will be close to 25. Otherwise, the mean will be, will still be a little bit different from 25. Then for the second one, let me put it again mean 2, and then let me put it again mean x1, x2. Now, and then I will print that one mean 2, and then let me see how we can see the means. So now we have 25 minus 26, but now if I have the mean difference, so let's say if this is in the control group, and if it is in the intervention group, let me just call it intervention group, the mean difference would be the mean at the control group, I mean the mean at the intervention group, which is mean 2 minus the mean at the control group. So that means mean 2 minus mean, which is very easy thing to do. And then now we have we can have a mean difference, we can print it out, and then we see how mean difference is calculated, or at least reported in individual studies. And then once you have the mean difference, the next thing that we want to calculate is pooled standard deviation. The pooled standard deviation, since we already created a function, let me just call it actually our function, it's just a function, it needs to return some value. So let me add then the function will return a pooled standard deviation. Now I should rerun it again. So as pooled function N1, the pooled standard deviation requires 4 different parameters. That means sample size in the control group, sample size in the intervention group, and then standard deviation of the mean of the control group, and then standard deviation for the mean of the experimental group. Now, once I have that, the next thing I do is SD pooled. Let me just call it SD pooled, and then I can give it my function. Of course, I created SD. What did I call it? S pooled. Okay. So let me just use S pooled function, and then after that, the first thing I need to do is N1, N2, and S1. So N1 is at 100, N2 is also already defined to be 100, and then S1 again. S1 is about 5, and S2 is about 3.1. Then once we have that, we can create our standard deviation. Now we already have everything, and then we can run it. Now we already have the pooled standard deviation. That's the pooled standard deviation, and then so that means studies will report this kind of value. So the change, the mean change was mean difference of how much was it? Minus 5 point approximately minus 5.7, minus 5.8 actually, minus 5.78. Let's move around. So we have that minus 5.78, and the pooled standard deviation will be about 4.16. So these are the kind of values that studies will report for you. These are the values that you need for your meta-analysis at the end. Yeah, so you need a mean difference in each study, and then you need the pooled standard deviation. But I will come back to the slides, and I will show you what you need for the meta-analysis. For the meta-analysis, to do meta-analysis of mean difference, one of the values that you need is the number of observations in the control group. That's N1. The way we define it as N1. But in the metan function, from the metan package, so that is defined as NE. Then a mean experimental group, that is the mean of the experimental group, and the next value that you need is the standard deviation in the experimental group, or the standard deviation for the mean, standard deviation for the mean of the intervention group. Then again, because it's group design, you also have another group, so we need all these 3 different types of values for the control group. So number of observations of the control group, and mean of the control group, and the next value will be standard deviation of the control group. Once you have these values, meta-analysis will be meta-analysis of mean difference would be simply putting the values and adding all the parameters in your function, and then the software will But again, the mean for continuous outcomes, it can really get complicated. It can really get complicated. Why? The problem is if you have randomized control trials, you usually have you may have like baseline difference and high pre-post correlation, and that's because randomized control trials will be badly randomized, or the control group and the mean, the control group and the experimental group might not be adequately balanced, and that's caused by usually reported from, that's usually from seen from small trials. If the trial is not a small size, then the chance of the baseline values to be similar is really unlikely. So you may have those kind of studies, bad quality randomized trials. So you have baseline difference. In that case, you have a problem. So for that, what you have, is your control group and you have intervention group. You usually have the control group, the baseline, so that means the mean of something. Let's say if you have the weight, so the mean of weight at the baseline for the control group, and then the standard deviation for the mean weight at the baseline, and that's again for control group. And then finally you have the follow-up values, let's say after 3 months of intervention. So you have like the mean of the mean weight after 30 months of intervention, or maybe at the intervention endpoint, and you have again standard deviation. Again, similarly for the intervention group, you have baseline mean, and then standard deviation for the baseline mean, and you have follow-up mean, and that means the mean at the intervention endpoint, and then you have the standard deviation for the mean for this value. So you have these values. For meta-analysis, I mean, if you are lucky, these values and the X control and the X intervention will be exactly the same. So that means if you subtract this to this, it will be 0. So that means you don't worry about these values. So you don't worry about these values, you cancel these ones, and you only work with these ones. So that means Y control, Y intervention minus Y control. And that's called simple analysis of final values, actually. It's called simple analysis of final values. You don't care about the values because they are 0, they are adequately but perfectly balanced. So that means you simply subtract the Y intervention minus Y control. So that's called actually simple analysis of final values. If you are lucky, studies in your meta-analysis, all of them are perfectly balanced, then you don't worry about so you simply use the final values, and then you have the pooled standard deviation for the Y int and Y control. But if you have a little bit difference, again, if you have a difference in X, for example, if you are working with HbA1c, if the baseline difference with the control group is 7, and then again in the intervention group, if it is 7.5, that means there is a difference of 0.5, and that's not a small number. So for that, you need to account that. You need to account for that. To account for that, what you need is you calculate the difference of these values and then the difference of these ones. Or in other ways, you simply create the difference of differences. Difference of differences in a sense, you have Y control, I mean the mean difference in the control group minus the mean difference in the experimental group. Again, calculating standard deviation for all of these values is a way again more complicated because you have 4 different values. Maybe you can do. There are many different ways to calculate. I think 5 different ways are 5 different standard deviation calculation methods were suggested, but to be honest, for me, what I found easier is to find the pool standard deviation here and then another pool standard deviation, and again you may pull the pool of the pool standard deviation. That may be wrong, but there are many different ways of calculating standard deviation for simple analysis of change score, but rather complicated. Yeah, but again, this is not only baseline difference. This accounts only baseline difference. This one is baseline difference, so it accounts only baseline difference. It doesn't account high pre-post correlation. Sometimes you have studies, the final values or the values, the mean at the intervention endpoint is predicted by the value at the beginning of the intervention. That means you have the value at the value at the before intervention is correlated with the post intervention. So that means you have pre-post correlation. It could be high, maybe high like 0.6, 0.7, or maybe 0.9. So maybe it's highly correlated. In that case, you have a problem again. So that means you have high pre-post correlation, and then you have baseline difference. In this case, you have a problem. So for that, you need a Blackbeard approach. That's called the Blackbeard approach, and that's called ANCOVA adjusted mean difference. That's called ANCOVA adjusted mean difference. For the ANCOVA adjusted mean difference, you just then add a little bit modification. It's kind of regression coefficient for the simple analysis of change score. It's the same formula, but you add a regression coefficient, this beta value. But this beta value, calculating this beta value, at least from reported data, if studies reported ANCOVA adjusted mean difference for you, you're lucky. But it's very unlikely. Sometimes you have all the values, all the required values, and then you will be able to impute or at least calculate beta from the reported values, from the reported estimates. So the way you calculate beta is like this. So you have the pre-post correlation. That means you have pre-post correlation. So that means this pre-post correlation would be correlation value here, pre-post correlation for the control group, and pre-post correlation for the intervention group, and that will be the average of the two. So that will be the average of the two pre-post correlation values. So you get the average of the pre-post correlation values, and then you multiply it by the ratio of standard deviations in the experimental group divided by the standard deviation in the the control group. That's how you calculate. But again, you have a problem. If studies don't report this, that means this correlation, pre-post correlation value, then you have a problem. You need at least if they don't report it, then you need necessary values or necessary parameters that are important to calculate. These are the values. For that, you need this kind of formula. There is also another formula, but I don't want to get really too much detail on this. But this approach is called Blackbeard approach if you have this problem in your studies. The way you calculate R is like standard deviation, baseline standard deviation, and then follow-up standard deviation. And then you subtract it standard deviation for the differences, like y int minus y control. So this will have standard deviation. And then you divide it by multiplication of all of these three different standard deviation values. And then once you get that, you can put it here, and then you get your beta values. So once you have the beta values, it's easy. You can simply modify it. Yeah, that's how it works. So it's I have some papers. I myself have published one paper on this. So if you this paper is actually written. I mean, the methodology of this paper is mainly with Ankuba adjusted mean difference. It's yeah. So kind of, and also we have also written actually. Maybe I can put it for you. Maybe if you are interested, I have all these really relevant references for calculating what you call this Ankuba adjusted mean difference. There are really some nice references, also some Excel functions in Excel if you are more comfortable with like putting imputing the values in Excel, for example, as I did back in 2018. I was calculating most of the values in Excel using T inverse normal CM function in Excel. But now I wouldn't do it in Excel. I would simply do it in R. So let me just show you one of the some of the values that I had in my meta-analysis paper. So you have n control, and then that means the number of samples in the control group, and the number of observations in the intervention group, and then you have the mean, baseline, and then standard deviation for the control group for this mean, and then you also have x int, that means the mean of the intervention group, and then you have the standard deviation. These are all for the baseline. So that means you have all these values for the baseline, only for the baseline. Still, we didn't reach the intervention endpoint. Yeah, and then you have the sample size. These are actually in the metan function from the metan package. These are the values you need for doing the meta-analysis. But that means you need to ignore all the baseline values and simply work on the intervention endpoint. That means simply the final values meta-analysis. That's what the metan function gives you, because we already said here, if I remind you, these are the values you need for doing the meta-analysis. So these are not enough, because if you have this kind of problem, because you need to adjust for the baseline difference, then you need to pre-calculate. You need to pre-calculate this mean difference and standard deviation, and then once you have the pre-calculated mean difference, you can kind of pull them. Anyway, the first thing before you decide whether to use simple analysis of final values, change score, or Ankuba, is what you need to do meta-analysis of baseline. The baseline difference. So that means the baseline difference. For example, we have 8.38, 9.02. You subtract. For example, in this case, I have 0.64 difference, which is really high. But for the other perfectly balanced studies, I have 0. So that means I'm fine with some of them. But again, for some of them, there are red margins. So here, I don't mind that much. But again, 0.3 is rather high. Yeah, so what you need is meta-analysis of this baseline difference. So I need these values, and I pre-calculate this, and then I do meta-analysis. And then if the meta-analysis of these values, if it is close to zero, you can simply work on simple analysis of final value. In fact, you can work in any of them, and still the meta-analysis, the pooled result will still be the same. But for easy, to make it more easy, I would simply work with simple analysis of final values. And that's as I suggested you to use only these values, and then the software will rule it for you. Yeah, that's all for between group mean difference. Next, I will talk about standardized mean difference, and maybe later about within group mean difference, especially for studies like pre-post, before after studies. For those, we may talk about within group difference. That's all for today. Once we finish all these theoretical things, effect sizes, because you need to understand before you combine studies. Then we will continue in our next session. Until then, thank you very much.